In this video, we solve problems from quiz number 7 from the fall 2020 semester. And we're going to solve the first 3 problems. Those are all problems that are associated with the standard L24 in our course, which is about the definition of the Laplace transform. So we start with a problem that looks like this. And we're given the graph. The axes are labeled. That's 0, 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. So each tick mark in the t direction represents 1 unit, and each tick mark in the y direction also represents 1 unit. So we've got this piecewise continuous function here, and we're asked to write f of t as a piecewise function. In other words, we're asked to write it in this form. Then after we do that, we're asked to use the definition of the Laplace transformation to compute the Laplace transform of our piecewise function f of t. And that's the first problem. The second problem deals with using a table of Laplace transforms to find the Laplace transform of each of the functions, and then using a table of Laplace transforms in partial fraction decomposition to find the inverse Laplace transform of the function. So that's the plan. I'm going to work this out on my paper for you. We'll start with the first problem. Okay, so this is our function f of t. And clearly it's constant on the interval from 0 to 4. We see that the constant value of the function is 3. So I would write this. F of t is a piecewise function. It has 2 pieces. On the first interval from t equals 0 to t equals 3, or sorry, t equals 4, the value of our function is y equals 3. So we'll write that way. And then on this interval, we see that we have just a line or a ray, part of a line. And that is for t greater than or equal to 4. So you can use t between 4 and infinity if you want to, or you can just write t strictly greater than, or no, greater than or equal to 4. Then we just need to find the equation of this line. Well, in order to find that equation, I would use the slope, or I would use the fact that slope is equal to rise over run in order to find the slope. We go up 2 and then over 2 in order to get from the point x or t equals 4, y equals 3 to the point t equals 6, y equals 5. So the slope must be 1. So this is 1 times t plus a constant. And to find the value of the y-intercept, there are lots of ways you could do that. You could just follow this pattern backwards. So we could go down 2 and over 2 and down 2 and over 2. And we would see that our line should cross the y-axis at y equals -1. So that's one way of doing it. And you could also use the fact that y is equal to t plus b for some unknown b, and when y equals 5, t is equal to 6. So solving this equation for b, we have b must be 5 minus 6, which is -1. So we get that value there. Okay, so that was part A, and there were 2 ways of doing that. Let's look at part B. So in part B, we're asked to use the definition of the Laplace transformation to find the Laplace transform of f of t. So this is a piecewise function. So this integral from integral from 0 to infinity that we see in the definition of the Laplace transformation can be split into 2 pieces. Now remember what the definition of the Laplace transformation is. It's the integral from 0 to infinity of e to the negative st. You take that and you multiply by the function that you're operating on, and you integrate with respect to t. So the value of this integral is a function of s. We call that f of s, and that is the definition of the Laplace transform of f of t. Now in our case, f of t has 2 pieces. In one piece, it's defined on the interval from 0 to 4. So rather than integrating from 0 to infinity, I will integrate from 0 to 4. And then I will integrate from 4 to infinity. And in each case, I want to put the definition of f of t on that interval right there. Well, on the interval from 0 to 4, f of t is equal to 3. On the interval from 4 to infinity, f of t is equal to t minus 1. So this is just a regular integral. So we can anti-differentiate, plug in the bounds, and subtract. That's just using the fundamental theorem of calculus. So I'll bring my 3 down. The antiderivative of e to the negative st with respect to t is e to the negative st divided by negative s. Because I'm thinking of that negative s as a constant, the derivative of e to the negative st would be that exponential times the derivative of the inside, which would give us a negative s. If we're taking the antiderivative, rather than multiplying by negative s, we'll divide by negative s. And then we will evaluate this from t equals 0 to t equals 4. Remember, these bounds go with this variable. And if we factor out the negative 3 over s, this is what we get. We have e to the negative s times t, where t is 4, minus e to the 0, which is 1. Okay, so that's what we have there. And then over here, we have an improper integral. Remember, every improper integral is really the limit of a proper integral. Since I've got an infinite upper limit, I will replace that upper limit with b and take the limit as b goes to infinity of the corresponding proper integral, the integral from 4 to b of t minus 1 times e to the negative st dt. And that's always how we evaluate an improper integral. We write the improper integral as a limit. It's the limit of a proper integral. And then you evaluate the proper integral. And typically that requires us to use the fundamental theorem of calculus. And I'll abbreviate that FTC. Now in this case, when I am anti-differentiating this function, I notice that I've got a polynomial times an exponential. So this is a good candidate for integration by parts where u is equal to a polynomial. Since that's the case, I think tabular integration by parts is the best way to go. U is the polynomial, dv is everything else. Now when we use tabular integration by parts, we usually don't write the dt over here. It's just the way it's typically written is this way. And we take the derivative of this polynomial u until we get 0. So we take the derivative once, we take the derivative twice, now we've got 0. Now we have 3 rows over here. We want to have 3 rows over here so that both columns have the same number of rows. And we'll anti-differentiate e to the negative st. When we're anti-differentiating, we've got to divide by negative s every time. So we divide by negative s once, which is the same as multiplying by negative 1 over s. And then we do that again. And then for tabular integration by parts, don't forget your sign convention. You want to multiply across the diagonal, and then you want to add, and then multiply and multiply by negative 1 and add. And that is the antiderivative of this function. We need to evaluate it from 4 to b in order to use the fundamental theorem of calculus. And this is still there. We're going to add that later. And I'm really leaving that limit as b goes to infinity alone, but it's still there. If I want this to be equivalent to this, I need to include that limit. So we'll have this times this minus 1 over s squared times the exponential. We're evaluating that from t equals 4 to t equals b. Now what I would recommend is writing this with a single exponential as a factor. So we're going to factor out the e to the negative st. So we'll have negative 1 over s times t plus 1 over s, if I distribute that negative 1 over s, minus 1 over s squared, times e to the negative st, which I could write as e to the positive st in the denominator, evaluating from 4 to b. And then I will replace my t's with b's. And then replace my t's with 4. And we subtract. That's the fundamental theorem of calculus. And the last step when you're evaluating an improper integral is to evaluate that limit. So you might need to review some content from Calculus 1 involving infinite limits. We need to know how to compute the limit as b goes to infinity of this expression. Well, there are no b's in this. The limit of a constant is just the constant, so we're just going to have this as a factor. But this part, well, it has this behavior. Let's assume that s is positive for right now. If s is positive, as b goes to infinity, the numerator or the denominator goes to infinity. The numerator goes to, well, that's going to be a negative number times something really large, so that's going to go to negative infinity. So this is a negative infinity over infinity indeterminate form. If I want to evaluate that limit, I can use L'Hopital's rule. So this limit is equal to this limit by L'Hopital's rule. You take the derivative of the numerator with respect to b, and you take the derivative of the denominator with respect to b. And we still have this expression over here. If you want, you could distribute the negative. So I'll have, this is negative 4 over s plus 1 over s is negative 3 over s. Negative 3 over s times that negative 1 is going to be positive 3 over s plus 1 over s squared. And we'll bring that negative e to the 4s up to the numerator. As b goes to infinity, I have a constant over something that's getting really large. So this will be getting really small, provided that s is greater than 0. That was our assumption. Now, if s is negative, then we would have, as b goes to infinity, this numerator would be going to infinity, and this denominator would be approaching 0. So you'd have some very large positive number divided by a very small positive number. An infinity over 0 is not actually an indeterminate form. That's actually going to infinity. Think about taking something very large and dividing by, say, 1 over a million. If you're dividing by something very small, dividing by 1 over a million, for example, is the same as multiplying by 1 million because you flip that fraction and you multiply. So if you have an infinity over 0 indeterminate form, it's not really indeterminate. It's infinity over 0 actually approaches infinity. So if s is negative, this would approach infinity. If s is 0, this would be undefined. If s is positive, this goes to 0. So the value of the Laplace transform of our function f of t is this expression plus this expression for s greater than 0. So let's write that on the next page. So that was negative 3 over s times e to the negative 4s minus 1. And then we had, that was from this expression. And then we have this expression here, 3 over s plus 1 over s squared, that quantity times e to the negative 4s. And if we distribute that negative 3 over s here, and we distribute the exponential here, you see we have a cancellation. These terms are the same, but with opposite signs, so they reduce. So the Laplace transform of our piecewise function is 3 over s plus 1 over s squared times e to the negative 4s. Okay, so for the standard L24, we would stop here. But we have learned about the Heaviside function, and we have learned how to take the Laplace transform of the Heaviside function, although that's not associated with standard L24. I think I'd like to check my work using the Heaviside function. So we know that f of t is 3 on the interval from 0 to 4, and t minus 1 on the interval from 4 to infinity. We know that can be written in terms of the Heaviside function this way. This is 3 minus 3 times the Heaviside function at t minus 4, because I'm turning off the function 3 at t equals 4. Then I'm turning the function t minus 1 on at t equals 4. So we have that. And if I want to, I can simplify. I'll have 3 here. Then I have minus 3 times this Heaviside function plus t minus 1 times the Heaviside function. So t minus 1 minus 3 is going to give me a t minus 4 times the Heaviside function at t minus 4. The Laplace transform of that is the Laplace transform of 3 plus the Laplace transform of t minus 4 times h of t minus 4. And we see that the Laplace transform of a constant is from our table. Laplace transform of 1 is 1 over s, so the Laplace transform of 3 is 3 over s due to the linearity of the Laplace transformation operator. And then this expression can be evaluated in this way. If this is h of t minus a and this is f of t minus a, we see that a is equal to 4 and f of t minus 4 is equal to t minus 4. So whatever you put in is exactly what you get out. So that means that f of t must be equal to t. Well, our theorem for the Laplace transform of f of t minus a times h of t minus a is this. We get e to the negative as times the Laplace transform of f of t. So in this case, we'll have e to the negative 4s, s should be multiplying that 4 up there, times the Laplace transform of t. And the Laplace transform of t is 1 over s squared. Remember, the Laplace transform of t to the n is n factorial over s to the n plus 1. If n is 1, we'll have n or 1 factorial over s to the 1 plus 1. So we get 1 over s squared. So using the definition, we found that the Laplace transform of f of t was equal to this. Using the Heaviside function, we find that the Laplace transform is equal to this, which is the same thing. We could factor out that 1 over s squared if we wanted to. So that's one way that you can check your work for problem number 1. That's not necessary at all to solve that problem. We just wanted to check. And that's something that you can do if you decide to reassess over this topic on a quiz. Okay, let's look at problem number 2. So number 2, we're asked to use the table of Laplace transforms to find the Laplace transform of each of the given functions. And this is our first function. Now remember our linearity property. If you have a constant times f of t plus a constant times g of t, the Laplace transform of that is a times the Laplace transform of f plus b times the Laplace transform of g. Or in other words, this is a times f of s plus b times g of s. So that means if I have a sum or a difference of a number of terms here, we can just take the Laplace transform term by term because this operator is linear. Other things that we'll need for this, I've got powers of t, so I'll need that the fact that the Laplace transform of t to the n is n factorial over s to the n plus 1. You don't have to memorize any of these. These are all in your table of Laplace transforms. I've got an exponential, so I'll need the fact that the Laplace transform of e to the at is 1 over s minus a. And then for this constant, I need the fact that the Laplace transform of 1 is 1 over s. So when we compute the Laplace transform of f of t, we'll get this. We'll have 2 times the Laplace transform of t to the 4th. So that is t to the n with n equals 4. So according to this rule, we're going to have 4 factorial over s to the 4 plus 1, which is s to the 5th. Then we will add the Laplace transform of t to the 5th. So n equals 5. So we'll have 5 factorial over s to the 5 plus 1, which is s to the 6th. Then we bring the constant down, -1. Then I recognize that as e to the at with a equals -9. The Laplace transform of e to the at is 1 over s minus a. So we're going to have 1 over s minus a, which is -9. And then the Laplace transform of 2 is the same as 2 times the Laplace transform of 1, which is 2 over s. So that's our answer. It's just not simplified. 4 factorial is 4 times 3 times 2, so that's 24. 24 times 2 is 48. And then over here, we're going to have 24, that's 4 factorial, times 5. So what is that? 120. And of course, subtracting a -9 is the same as adding 9. We have that there. It's nice and easy, just straightforward application of these rules. Got 1 here, 2 here, 3 here, and then 4 here. Okay, now let's look at our next one. We call this function g of t. And g of t has this form. It's e to the t minus e to the -t squared plus hyperbolic sine of 3t plus hyperbolic cosine of 4t all divided by 3. Now for these exponentials, I can use this one. For the hyperbolic sine and hyperbolic cosine functions, I need a couple more rules. We know that the Laplace transform of the hyperbolic sine of kt is k over s squared minus k squared. And the Laplace transform of the hyperbolic cosine of kt is s over s squared minus k squared. Okay, so I think this one, and this one will allow me to evaluate this. The first thing that I would do though is square this. If I write this twice in FOIL, or I can just use that identity for a minus b quantity squared, we're going to have first times first, it's going to be a squared. Remember with exponents, when you're multiplying them, you add the exponents. That's e to the 2t plus outer times outer, e to the t times e to the -t. When we add the exponents, it's going to be e to the 0. So we're going to have -1 times e to the 0, which is -1. Minus inner times inner is the same. It's -1 minus 1. It's going to be -2. And then last times last is a negative times a negative. That's a positive. E to the -t times e to the -t. Add the exponents and you get that. So we have that right there. And then the hyperbolic sine of 3t. We can compute the transform of this using this rule. And this one with the 3 in the denominator, I would factor out that 1/3. It's almost a distraction. It's just a constant multiplying our hyperbolic sine or hyperbolic cosine of 4t. So I'm going to end up using the e to the at rule, the Laplace transform of 1 rule, the hyperbolic sine rule, and the hyperbolic cosine rule this time. So for e to the 2t and e to the negative 2t, my a's are equal to 2 and negative 2, and we'll use this formula. Here I have a hyperbolic sine of kt, where k is equal to 3, and a hyperbolic cosine of 4t, where k is equal to 4. And so this is what we get when we take the Laplace transform of g of t. We get 1 over s minus a, where a is 2. And then the Laplace transform of negative 2 is negative 2 over s. It's just negative 2 times 1 over s. And here we'll have 1 over s minus a. Subtracting a negative 2 is the same as adding 2. Then here, for hyperbolic sine of 3t, k is equal to 3. So we're going to have a 3, that's our k, over s squared minus k squared. And then over here, we'll have a 1/3 times the Laplace transform of cosine of 4t, or hyperbolic cosine of 4t. So we'll have s over s squared minus k squared. K is 4, 4 squared is 16. So we have that. And if you want, you could distribute that 1/3 to make that just an s over 3 times the quantity s squared minus 16. I would probably just leave that alone. And that is the Laplace transform of g of t. So we're just choosing the appropriate rules and then applying them here. Now let's look at the next problem. Now this is our last problem for standard L24. It asks us to use the table of Laplace transforms and partial fraction decomposition to find the inverse transform of this function, f of s. So I noticed that I've got this 3rd degree polynomial in the denominator here. And if we look at our table of Laplace transforms, there's nothing that says, you don't have anything in that right-hand column that says if the denominator looks like as cubed plus bs squared plus cs plus d. It never looks like that. The denominators typically look like s minus a or s minus b, or they have the form s squared minus k squared or s squared plus k squared, or maybe the s has been replaced by an s minus a or something like that. But we never see anything that looks like this. So to make this look like the Laplace transforms in our table, we're going to use partial fraction decomposition. So I would start by factoring that denominator as much as possible. I would group these two together and these two together, and then see what we get. If I group these two together and I'm factoring out any common factors that I see, s cubed and s squared have an s squared in common. Then I just ask myself, s squared times what will give me s cubed? That's a single s. And s squared times what will give me a positive s squared? It's just a 1. Now over here, we want to factor out whatever 4s and 4 have in common. That's a 4. I ask myself 4 times what will give me 4s? That's just an s. And then 4 times what will give me a 4? That's just a plus 1. So now I'm looking at this group and this group. This is called factoring by grouping. And I'm saying to myself, what do the groups have in common? Well, the groups have an s plus 1 in common. So this is the same as this. I'm leaving my numerator alone. I'm just sort of bringing it along to keep everything equal. And then I'll factor out the s plus 1. And then in the second set of parentheses, I'm saying to myself, s plus 1 times what gives me this? It's an s squared. And then I say s plus 1 times what gives me this? Plus 4. So that is the factored form of our denominator. And now we see we have an irreducible quadratic factor, s squared plus 4, and we have a linear factor that's not repeated. So I can write the partial fraction decomposition of this expression this way. This is a over s plus 1 plus b s plus c over s squared plus 4. And now we just need to find the values of A, B, and C that cause this expression to be equal to this expression. In order to do that, I will take this and I'll multiply by the LCD. So that LCD is s plus 1 times s squared plus 4. We're taking every term and we're multiplying by that LCD. And then we simplify. S plus 1 over itself is 1. S squared plus 4 over itself is 1. The s plus 1's reduce here. The s squared plus 4 will reduce there. And then you're left with this equation. You've got 2s squared plus 2s plus 10 equals a times the quantity s squared plus 4 plus bs plus c times the quantity s plus 1. Now, typically, we like to choose values of s that cause each of the factors to be 0. But we don't tend to choose complex values of s. So we're not going to let s equal plus or minus 2i to cause this factor to equal 0. But we will let s equal -1 to cause this factor to be 0. And then we'll use that to solve for one of the values of a, b, and c. So when s is equal to -1, this factor is 0. So we'll have 2 times -1 squared, which is 2, plus 2 times -1, which is -2, plus 10 equals a times -1 squared, which is +1, plus 4, plus bs plus c times the quantity -1 plus 1, which is 0. So we end up with 10 equals 5a, which means that a is equal to 10 divided by 5, which is 2. Okay, great. Now you want to pick a value of s, any value of s from here, in order to try to find b and c. I would choose s equals 0 and s equals 1 because expressions are really easy to evaluate at s equals 0 and s equals 1. So when s equals 0, we'll have 0 plus 0 plus 10 on the left-hand side. Then we're going to have 4 times a here, plus b times 0 plus c, which is just c, times 0 plus 1. And we already know that a is equal to 2, so that means that we have 10 equals 8 plus c. And if we subtract 8 from both sides, we see that c must be equal to +2. So now we know that c is equal to 2 and a is equal to 2. So we'll just pick another value of s to try to find b. I would use s equals 1 because that's pretty easy to evaluate. It's very easy to evaluate any expression at s equals 1. So we're going to have 2 plus 2 plus 10. If s is equal to 1, so it's going to give us a 14, equals 5a plus the quantity b plus c times 1 plus 1, which is 2. Now we know that a is equal to 2. So we'll have 14 equals 5 times 2, which is 10, plus b plus c, so it's b plus 2 times 2. So if I subtract 10 from both sides, I have 4 over here equals 2b plus 4 if we distribute that 2. And if we subtract 4 from both sides, we see that 2b must be 0, so b must be 0. Okay, great. So we know the values of a, b, and c that cause this plus this to be equal to this. So that is the partial fraction decomposition for our f of s. So f of s is equal to a over s plus 1 plus bs plus c over s squared plus 4. Since b is 0, that's going to be 0 times s plus 2 over s squared plus 4. And that's great. Those look like two formulas from our table. So I have the Laplace transform of e to the at is 1 over s minus a, and the Laplace transform of sine of kt is k over s squared plus k squared. So this looks like 1 over s minus a, where a is -1. And this one looks identical to this with k equals 2. Now this one's not exactly identical. Guess we could factor out a 2. So that's 2 times 1 over s plus 1 plus 2 over s squared plus 4. If I want the inverse Laplace transform now, that's the inverse Laplace transform of these expressions. The inverse transform of 2 times this function is 2 times e to the at, where a is equal to -1, so it's e to the negative t. And then we're adding the inverse Laplace transform of this, which is sine of kt, where k is equal to 2, so it's sine of 2t. So that is our f of t. And those are the solutions to the quiz problems from quiz number 7 that are related to that first standard, L24, which is the Laplace transformation defined.